So without further ado, the next speaker, if I can find his presentation, I think it is here, is looking at wind turbine development for harsh climates. Alex is someone who's been in the wind industry for quite some time, spent a number of years at NREL, the National Wind Technology Center, looking at small turbines and power electronics, then moved off to Europe and spent some time in Spain, if I remember correctly, and then is now currently a principal with 3E, which is a wind turbine siting development company with lots of experience in wind turbines, primarily in the European market. Alex.
Thank you, Ian, for this introduction, and thank you for giving us the opportunity to present our wind turbine concept here at this conference. It's been a great experience, and it's a great place to learn. And although I'd like to see this industry grow, the fact that it's still this size makes it possible to learn from each other, and information is flowing more openly than at these large conferences that we see organized by UIA and OEA. So what I'm going to talk about is a new wind turbine concept, and the picture you see here is actually what in part inspired us. This is one of the projects on PER list, and it had a yes on the column saying whether this system was operating. Unfortunately, I had to say to PER it's a no, because this turbine standing on the island of Brava has been installed in '96, has been working until '99, and since then has been standing still for a simple failure of an hydraulic actuator that has to retract the tip wings. So these are the kind of conditions that we've seen throughout 3E's activities as a hybrid system integrator. So I'll talk briefly about the background of this project, the design drivers, what has key aspects that we've taken into account when designing a turbine for this market. I'll explain the technology, what the status is of the project now, and some conclusions. So maybe just a brief introduction of 3E. We're a consultancy based in Brussels, Belgium. We have now representatives in various places in the world, among them China, South Africa. We have an office in Turkey also, and a large office in France. We're about 100 full-time equivalents now. Our services in wind, as Ian already explained, are focusing on helping project developers getting projects online. So we do everything from starting from site assessment, wind resource assessment, getting the permits done, helping them make bankable projects, and now we're slowly moving into the operational phase with some dashboards we're developing for project developers. So our client base typically is either the people developing the projects or the institutes providing the finance. Now, what have we been doing in hybrid power systems? We've been active in hybrid power systems throughout a series of projects. Most of them were not in harsh, well, they were in harsh climates, but not climates you would think of as particularly cold climates. More high temperatures were the challenge, dust, sandy areas, except for the one project on the South Pole. Most of the projects were based in developing countries. And unfortunately, the large majority of these projects, they got stuck at the phase of feasibility. Very often, the numbers are there, the economic viability is there, but the funding is lacking to really make the project happen. So I'll just briefly introduce three of the more illustrative projects that we've done. One of them is in Timbuktu, Mali. Very nice project. They have a village on this emblematic location that is fed by a diesel genset power station. They have 4 diesel gensets there. Electricity is sold by the local utility, Électricité du Mali, at a rate that is horribly expensive, seeing the income levels of the people over there. And even then, the utility is unwilling to expand the diesel station because it's not self-supporting. It's economically not a viable plant. So we've done a study. We've been doing wind measurements on the sites for over 3 years now. We've done a very detailed technical economical feasibility. We've written a complete project plan. And still we see that these projects are not happening, just because utility is not willing to invest. There is no private player who's willing to invest in this, and there is no funding available. We're now going through a series of, let's say, attempts to gather funding for this project through African Development Bank money, United Nations development money, but it's hard to make these projects happen. One project that did happen was a project in the main harbor of Cambodia, Sihanoukville. They had an unreliable power supply for the harbor based on very old diesel gensets. They wanted to modernize the system and hybridize it. So we've been doing the site assessments. We've been doing the sizing of the system using Homer, among other tools. We've selected a system configuration, and we went throughout the whole tendering procedure. So this was really bringing down the, let's say, the initial system concept down to writing detailed specs of components, having manufacturers offering their products, and actually bringing the system together. So this system is now in operation for over a year and a half. It's been operating quite well. There's been a lightning strike on one of the blades that needed to be repaired, but apart from that, this is a quite successful project. And then I'll mainly skip this project because it was explained yesterday a bit with the presentation from Proven. We've done the concept for this research base, Belgian research base at the South Pole, where we did the complete concept. And that was interesting because it had to integrate both the heat demand and the building as well as the electricity demand. So there was a holistic approach to doing an all renewable project on the South Pole. Now, the things that we've seen by being in this industry as a system integrator, as a company trying to dimension size and select optimum configurations, is that especially if you look at projects in the developing world, overall investment cost is still too high. And that's not because of the technology mainly, but because of the other costs associated with bringing this technology on site and installing it. A lot of the projects are still custom engineered. There's no systematic approach to these demands. Very often you need rather complex balance of plant components, which further increase the costs. Foundations can be a problem, both here and also in very sandy areas like the Sahara. And transport and installation, also both here and in developing worlds, are really a challenge, and they can bring the cost up to levels where it's really not economically feasible anymore to put turbines or PV systems on those locations. Secondly, we think reliability still is an issue. Not that turbines are unreliable, but turbines need maintenance. And very often this maintenance is overlooked. Institutional issues are not well taken care of, and there's no clear incentive. There's no ownership to maintain these turbines properly. And then you see things happening like on the island of Cabo Verde, where a very simple repair just does not get done. And thirdly, we think that these turbines are often located not where the wind blows mostly, but very close to the load or close to the diesel plant. So we really need to have turbines that have power curves that are really very efficient at low wind speed sides. Still, they have to be able to cope with very extreme conditions. So it's a combination of having a low wind speed rotor that can cope with very extreme storm conditions. So what have we done? Then we set out to design a turbine specifically for these applications, and we said, okay, what are we going to take as let's say basic drivers for our design? We think reliability is key because your overall downtime is determined by your mean time between failure and your mean time to repair. If your mean time to repair is going to be very long because there is no incentive, there is no skilled personnel, then as a wind turbine manufacturer, you can at least make sure your mean time between failures is significantly high, so you have less failures. So we wanted to build a very simple, robust turbine. We think also that it's true one size fits all is not the correct answer, but maybe few sizes fits all. Maybe you can build a modular system and you can pre-engineer, pre-package all components necessary to do wind diesel and have a modular approach and build several sizes, but pre-build them and pre-engineer them instead of doing custom engineering for every project. The logistics, very important. We've heard here ratios of 25% turbine cost versus 75% everything else cost. This is really a ratio that has to be improved, we think. Turbine costs are what they are, but the overall project cost should come down by bringing down these other costs. And then, as already mentioned, we were going to design for low wind speeds. This should bring us to an overall lower investment cost, a lower operational cost, a higher yield, which at the end of the day makes these projects more economically attractive. So this is a picture of the design we've come up with We call it exant, extremely austere, nimble, yet tough. There's other explanations for this. We think it reflects the philosophy and the product. I'll go a bit deeper into the technology. So one of the concepts is that we have fully integrated the drivetrain into the structural components. So being an electrical engineer, I know how simple an electrical machine can be, and it's basically just rotating magnets, creating a rotating flux over some coils. So we just put the coils on the stator frame, put some electrical steel around them, screw the magnets to the inside of the hub, and that's becomes a generator for a wind turbine. So you fully integrate your generator components. You only have one single rotating component. You can work with slightly higher tolerances to assure air gap is not a problem. You have an overall lower parts count, obviously. There is no need for any alignments, and it's a machine that's very easily repaired and replaced. Reliability. The graph below gives you an overview. It's hard to read, but it's basically some of the results of the Rely Wind project, which is a European Union-funded project that has been done with some of the wind turbine manufacturers, gathering statistics on failure rates of components. And what you see indicated in red are the usual suspects, the typical servo systems of a pitch and yaw drive. Although they can in principle be very simple, they tend to be complex systems located at locations that are harsh conditions, rotating, very hard to make them completely waterproof. So these are components that have rather high failure rates. The gearbox is also in there, and then there is also the frequency converter. So a lot of controls, electronics, these systems tend to fail, which is not a problem for wind turbines that are easily accessible. But even this simple failure can create a very long downtime in a very remote region. So we said we have to eliminate as much as possible these systems. So we've actually, this design is undergoing certification now by Germanische Leute, and we've had long discussions with them. Do we really need this sensor? Can we replace it with some other measurement? Does this redundancy of this sensor can be incorporated by looking at some other signal that we can then interpret as a measurement for this? So by doing that, we've significantly been able to significantly reduce the number of sensors. And every sensor you can take away is a connection that you can take away, is a possible source of failure you take away. Of course, we need power electronics, we need control electronics, but we've put them in a very controlled environment. They're no longer in the cell, they're not in the tower, they're in a nicely controlled environment sitting next to the tower. So we think there is the right place for power electronics, and this is where they can survive longer. So the benefits of this is that you need less maintenance because you have less components that wear, you have less components overall, and I think you'll see an improvement in reliability because of fewer connections. We think, as already said, that balance of plant should not be an after, let's say, something that needs to be engineered once the wind turbine has been integrated into the system. But the wind turbine could come with its balance of plant. So you could integrate dump loads or useful loads for excess power, short-term storage into your device. So this means your interface to the existing, because I'm mainly focusing on retrofit installations, your interface to the existing diesel network becomes a very simple connection. And a lot of the errors that happen with these systems happen during commissioning, when things are brought together. So the simpler your interface, the less source you'll have for errors in that phase. Transport, especially here, we see that transport is a very high, can be a very high cost. We've been able to design a turbine that fits in one single 40-foot container, which we've seen throughout, even in the developing world. This is something that gets basically everywhere. We've limited the component weight, so once the container arrives on site, you also do not need any heavy equipment unloading it. So we basically can erect and install and transport these components just using a trailer and a four-wheel drive. So this makes this turbine very suitable for complex terrain, complex sites, where there is hardly any decent road infrastructure, and you don't need to bring in any heavy cranes to erect and install this turbine. We want it to be innovative. Obviously, we want to build something that has that uses smart solutions for these problems, but we don't want to be exotic. So throughout the design process, we've talked to our component suppliers, to our material suppliers. We need to be able to source these components from as many places as possible. So don't give us any solution, don't give us any material technology, manufacturing technology that is very exotic. We'd rather then go for a more low-tech, widely available solution than going for something that is too high-tech. So we think that gives you the benefit of giving you an overall lower cost in turbine, because the more sources you have for your components, the lower your cost you're going to get. And you can just easily control your supply chain by having a global supply chain and by having multiple suppliers for each component. So blades are just regular layup technology. The magnets are obviously rare earth materials, but there's nothing too exotic about that anymore. Some of the structural components are just taken from the steel industry, just regular steel tubes with standard diameters, standard wall thicknesses. So a lot of this is based on standard components. The tower is obviously, in this case, it's a tilt-up tower if you want to erect without any cranes, so you can just do the assembly on site. Gives you a lightweight, low-cost solution. Also gives you the possibility to have smaller foundations, so you need one central foundation, and then you need 4 smaller foundations for the guy wires, because it's a guy tower. So overall, we believe this could be a lower foundation solution, lower cost solution for foundations. For the rotor, we wanted to design a rotor, as we said, that has a very good performance at low wind speeds. So you wanted to have a large rotor diameter. Still, we need to control the peak loads. And we've looked at the technique of aeroelastic tailoring to do this. Now, there's essentially 2 techniques. You can work on the directions of the fibers, or you can just use regular layup technology, yet regular orientations of your glass fiber mats, but you can use a different mold. And just by sweeping back the tip of the blade, you also get a similar effect that at high aerodynamic loading, you basically shut your peak loads and you can go up to higher rotor diameters while maintaining your load envelope. So this is a very interesting technology for low wind speed sites, where you can have a lighter structural component and still have a high yield at low wind speeds. We also put there as a benefit innovative looks. It might be surprising, but we actually had troubles convincing the people from Cambodia to install a 2-bladed machine. They thought it was not up to date, it was not state-of-the-art technology. They really insisted on having a 3-bladed one. So sometimes you have these rather strange drivers for selecting a turbine. So the power curve, we have a very aggressive power curve at low wind speed sites, at the expense of having a drop-off at higher wind speed sites. Now we know at 5, 6, 7 meter per second wind speed sites, the energy that can be generated above 20 meter per second is really insignificant. So we think this is the right choice for these applications. So this is a bit of technology, and then an overview of where we are now, because maybe you've seen we have a small stand there. It's a picture of it's an image of a wind turbine. It's not a picture of an installed turbine. So fortunately, we don't have any commercial product yet. We are now, as I said, we've submitted. We're undergoing Type D certification by Germanische Lloyd. We are in the process of prototyping the components, both blades, generator. The more exotic components will be prototyped and lab tested. We plan to erect a full-scale prototype by the end of the year, hopefully at the RISO Institute, which we've collaborated a lot with in Denmark. And then we should go through our field test and type certification, and by the end of 2012 we hope to have a fully commercial product. So a bit of the conclusions. We want this, with this design, we aim at bringing the cost down, because technology, has been said here, is not the problem, but it's that technology that is imposing a cost for all the other phases that come after once a turbine leaves the factory. So by designing a different turbine, we can have an impact on these costs, reducing the cost of custom engineering, reducing the cost of transport and installation, reducing cost of balance of plant. We also would like to see that the market of wind diesel should be able to expand beyond these pockets of markets where cost of energy is very high and financial incentives and subsidies are available to make these projects happen. There is a lot of communities out there in Africa and Southeast Asia that need this technology. But if we can bring the cost down to a reasonable amount of dollars per installed kilowatts, we won't be able to access these markets. So We need very reliable turbines that require little maintenance because your mean time to repair is going to be long, so your mean time between failure should be as long as possible. And as I said, we need turbines for these low wind speed sites because in the end it's about displacing fuel, and that means maximizing yield at low wind speed sites. I think that was it. So I'll be happy to take any questions if there are any.
Three questions, I guess. Realizing that you're still in sort of the prototype phase, do you have a target cost for a 100 kW machine, 40-foot shipping container ready to ship?
We think that the ex-works costs of this turbine should be below 2,000 euros per kilowatt, so 200,000 euros, which is comparable with, which is about, I think, $220,000 now, roughly, maybe a little bit more. Which is comparable with the turbines that are out there now, but the difference should be made once your turbine travels on site and is installed.
And do you anticipate a tilt-up tower in the future, or just the guide tower?
This is it's a tilt-up guide tower. Yeah, that's the.
So if you do maintenance, you have to lower the tower.
Yeah, all maintenance is done at ground level. Yeah. The target cost would be 2,000 euros per installed kilowatt. The numbers we've been hearing here for full project costs, they're actually up to $6,000, $7,000, sometimes up to $8,000 per kilowatt. So we think that the turbine cost should be 2,000 euros to $2,200 per kilowatt. And then once on site, this cost might double, but it should not triple or should not be 4 times.
The design, I noticed it seems a little lopsided to one side, so all the weight is off to the side of the tower. Is that how do you accommodate for that kind of design?
Yeah, we've looked at the pros and cons of that, but we wanted to include as much as possible passive systems, because the whole loop of measuring something, sending a signal to an intelligence control unit, and then going to an actuator is often a loop that creates that needs connections, needs different units to talk to each other, and is a source of errors. So we wanted to have a passive yaw system, which meant that we had to go downwind, which obviously means that indeed the thrust and the weight, they kind of add up, and you have higher loads on your tower that way. But that is a disadvantage that we thought is less, well, it's not insignificant, but we live with that because we get a more reliable yaw system in return.
Additional question?
How many kilowatts will your prototype be?
So this product is a 100 kilowatt turbine, and then later on the plan is to expand portfolio and have both a smaller and a larger machine.
Does ZAN 21 mean you have a 21 meter rotor?
Exactly.
And what is the hub height?
The hub height is 30 meters.
30 meters, thank you.
Additional questions?
What's that cost you gave us, the total installed cost and cost of the turbine? Question 1.
The cost of the turbine.
And tower?
And tower, yeah.
Do you have an estimate on installed cost?
But it's very site specific, I've learned over the past days.
Sure. Remote, highly remote. Let's say Western Alaska. Do you have any kind of estimates?
Well, we think you can ship a 40-foot container pretty cheaply now. Once it gets on site, we need a trailer and a 4-wheel drive to erect the turbine. Trailer, a 4-wheel drive, and a winch. So whatever the cost is of, let's say, 4 persons, 2-day operations, a 4-wheel drive, and a trailer and a winch. So.
So what do you think, how well do you think this is realistically going to hold up in extreme cold weather? Have you done any modeling or estimates on that at all?
We are designing according to the cold climate recommendations by GL, but Per just pointed out that it's true, they're not very demanding. We've seen here conditions that are way more demanding, but we're working at an operational temperature range of plus 50, minus 20 C. Our focus has not been it is on if off-grid market with diesel systems, but it's true our experience is mainly based in developing countries and not as much in very cold climates.
You mentioned off-the-shelf bearings and then yaw drive components. From what little I've looked at, it looks like bearings are made real specific and are made, I don't know, I was looking at like you'd have to get one was just from Finland. So that seems like that could be a problem with needing a part if you're out in very remote Alaska.
You know, we looked a lot at bearings because since we wanted to integrate the generator and basically your main bearing coincides with your generator bearing, it increases the size of your bearing. And we've talked to main bearing manufacturers and say, where is your bearing cost, where does it shoot up? And where is your delivery time, instead of becoming an off-the-shelf component, goes up to months? And we're right sitting at that knee point where we've maximized the bearing diameter because it gives you a more efficient generator, but we stay within ranges that they just say this is a standard product. You're going to find this with SKF, you're going to find this with Timken, you're going to find this all over the world. So we've looked at that very, very carefully.
Is that something really hard to replace? Because it can be a specific make you made?
No, these are standard bearing sizes you can buy from different manufacturers.
But you probably don't have to replace them very frequently.
No, I mean, we obviously designed for the full lifetime of the turbine. The bearing is dimensioned to cope with all the conditions during a 20-year lifetime.
Quick.